So my lab studies a condition called cardiac fibrosis, which probably most people have not heard of and are not familiar with, but affects a surprising number of people. So in cardiac fibrosis, we have a sort of a protein skeleton in our heart. It's not a bony skeleton, it's a very soft, supple skeleton, but it provides extra strength to the heart and helps make sure that our heart can take the pounding that it goes through every day. Our heart will beat 100,000 times a day. It undergoes these tremendous pressure swings. And so think of this as like a network of fibers that helps knit it all together and helps attach cells to one another, make sure that they can handle this kind of physical force. We've understood that fibrosis is a concern for many, many years. We've seen what it looks like for many, many years, although generally we've seen it on autopsy when you look inside a patient, look at their heart. Now we are developing new techniques that allow us to see fibrosis within the heart in a non-invasive way. So the patient goes in for basically a scan, and we can get a pretty good idea of how much fibrosis is happening in their hearts. And this is something that's just developing in the last few years, and that we're very excited to see, because it'll give us a better sense of how common this condition really is. Fibrosis occurs after heart attack. It occurs in response to high blood pressure. It can happen if you have valve disease. There are many conditions that can cause fibrosis. Considering that there are millions of people worldwide that have some sort of cardiovascular condition, the odds that they have fibrosis of some degree, probably some clinically significant degree, is pretty large. In my lab, we've been very interested in understanding the molecular signals that turn on these pathways to make more of this collagen. So this collagen, as I said, it forms these sort of bands throughout the heart. I like to think of, if you look at a street being built, you'll see rebars that are being laid down, and then they'll pour the concrete on top of that. And the reason why they do that is because concrete withstands compression very well. That's why it makes great roadways, because you can put heavy cars and trucks on it and it won't crush under the weight. But when we have spring and fall and temperature changes and the concrete starts to expand and contract, it doesn't resist those forces very well, and it tends to crumble. By putting rebar in, we help resist the tendency for concrete to expand and contract, and as a result, we've added strength to it by adding these iron reinforcing bars. The collagen fibers in our heart do a very similar job. They resist this expansion, so the heart doesn't blow out under pressure. But similarly, if we have too many, it then acts more like a cage and restricts the ability of the heart to do its job. So by understanding how that cage is made, how those collagen fibers are made, can we perhaps come up with a way to slow it down or to even stop it when there's too much collagen being made? And we've identified a new pathway that had never been looked at before in the context of the heart, where we've identified a particular protein whose job is to turn on the genes that encode these collagens. In other words, when we make more of our protein, we get more collagen as a result. And now we've got evidence that if we interfere with the role of our protein, we get less collagen. So we can tune it up and tune it down as we need to. And that's very exciting, because this starts to form the basis for a treatment. If we can target our protein with a drug or some other intervention, perhaps we can reduce the collagen burden. The very exciting thing is that we think the same pathway is involved in other tissues as well. So just as it forms these fibers in the heart, it can form similar fibers in the liver, in the kidneys, in the airways especially, for example, if you have asthma or obstructive pulmonary disease. These are conditions where fibrosis is associated, where we get these additional collagen fibers being made. And we're starting to build up a pool of evidence suggesting that our protein is involved in all these processes. So at the end of the day, what would be my greatest dream for where this could go? We'd come up with a medication that would be beneficial not only to cardiac patients, but also to patients suffering from kidney disease or liver disease or airway dysfunction.